All right, we are in. Good evening, everyone. This is Celso Batalha. I received a few questions regarding final exam. Final exam is on Thursday. That's the recommended. In fact, in our district, we are supposed to have a final exam in the last day of class, and since after graduation there is no class, so basically that should be on Thursday. Uh, but since our online class doesn't have a face-to-face meeting during the week, I'm kind of a flexible to have this final exam anytime you can, and anytime I have my other final exams going on. You can just show up to my regular physics or other astronomy courses and just take the exam there. Let me give you some preview. You can look in my office hours, and any office hours will do for exam as long as you have 1 hour um, total time for your exam. That's what I'm shooting for. 1 hour of exam, so you can come to my office hours. I have office hours on Wednesday that goes from 11:30 to 2 o'clock in the tutoring center in front of Physics Lab SA 111. That's one option. I have office hours early in the morning from 8 to 8:30, but I don't recommend because it's just 30 minutes. The nominal office hours is on Thursday, May 25th, from 10 to 11 in LE232, and that's the one you can find in my web. Um, you can go to that time, and I will be there at 10 o'clock. But you again, you can choose to do in any other time if it's flexible for you. Um, I will not be there. I will be giving final exam on the week before, on a Thursday, 20 no 18, on a Thursday 18 at 6:30. So if you want to do the final exam at that time, you can also attempt that from 6:30 to 9:30. So whatever time you decided to come, that is not Thursday, May 25th at 10 o'clock, email me and then I can make some arrangement with you. Now this week we have our midterm number 3 at Thursday, same um, procedure as the previous exams. It's going to be open the entire Thursday, and then you choose 1 hour, and then you do your exam during that hour, and I will reopen on Saturday for another shot if you want to. You don't need to, but I will open. So this week we have an Astro News. Oops, sorry. Where is it? There you go. So the Astro News is an article about a survey telescopes, and the seed. What I would like you to do is to read the story, of course, and try to explain what the telescopes will be used in this all-sky survey, but primarily explain what sort of outcome you expected to come out of the panoramic survey telescope and this rapid response system. So it's interesting because now, with the way the technology is evolving, and the way the ability of astronomers to collect not just data on one star or two star or a few groups of stars that happen to be together, but all sky survey, and to release this data to the public and have us using technology that we all have at home, like computers, to analyze this data. This is a new era in which not necessarily you need to have a degree to do research at home, and to be in contact with the real astronomical data, with and be able to use the skills you learn in astronomy introductory course, plus some skills that we might share with you, to really find out um, detailed information about sky objects. So basically what I would like to do is to read this article. It's kind of a short one, and then just to give your opinion on what sort of a outcome can come out of this panoramic survey telescope, and 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 when this data is finally released to the public, and people like me and you can have access to it, and do things with it. That's for Astro News this week. And we are getting close to our to closing our course. We have basically 3 weeks to go in subject in materials. And last week I didn't read and correct the discussions, and I have to do that. I'm kind of behind 1 week, and I apologize for that. And I will try to upgrade and update the grades of all of you in the next few days, and then get ready for the closing weeks of this course. So this week we are studying galaxies. So we are basically moving out of the domain of stars and going to the domain of hundreds of billions of stars, and try to make sense of what that is. So let me share the PowerPoint this week, PowerPoint. But before I think I open, yeah, let me show quickly here some pictures of galaxies in general. So galaxies are complex structures that have hundreds of billions of stars. And now, after we went through the chapters where we describe planets around stars, so not only hundreds of billions of stars, but also several trillions of planets maybe happen to exist in the realm of galaxies, of a galaxies. So just for a while, just think about our own Milky Way, which is a system of hundreds of billions of stars. And we know there is life in one of these stars, which is our sun, but why not in other places? And when we think about life, we kind of get tempted to think about aliens, like with intelligent life. But life is some structure that has the ability of reproducing itself and procreate and develop some sort of intelligence. And for that, you don't need to be a human, but you can be anything capable of exchanging energy with the environment and reproduce its own characteristics. And so life can be existing in the subsurface oceans around Enceladus or Europa, some of the major moons around that circle our Jovian planets. So we can find life there in the future, not so far future, but we also can find indications and footprints of life in exoplanets circling stars. And perhaps in our lifetime we might hear about this exciting part of astronomical research once the James Webb Telescope is launched in a few years from now. But I have pictures of few galaxies, and all the galaxies that I'm showing here, they are spiral galaxies. Some of them are not galaxies, they are just imagination things. But what spiral galaxies are? Spiral galaxies, in fact, there are 3 major classes of galaxies: the spiral, elliptical, and irregular. So our Milky Way is a spiral galaxy. And when you see this picture here, whoops, yeah, there you go. when you see this picture here, it's Andromeda, a spiral galaxy shows some bright center area, but also you see these dark lanes on it. So these dark lanes are areas where you have a gap of bright stars, hot stars, and the gas that happens in this to exist in this gap is not being light up, is not being radiated, is not being shown, and then it appears kind of a dark dust lanes. So again, spiral galaxies show these dark dust lanes as this one over here, and those are typically called spiral galaxies. Let me see if I can get more. There you go. This is this darkness. So this galaxy here, we are seeing edge on. So think about a galaxy that is not completely shown. So like here. So this is a galaxy that is almost top on. See this? This one, this little one over here is almost top on. And a galaxy that is seeing edge on is like this one. We are seeing through the edge, and then we are looking through the plane of the galactic plane that is populated with this dark dust lane. So what this dark dust lane is? So in previous chapters we found that our Milky Way, in fact in the region in between stars, is a region of low temperature, and there is a tendency for the material in there to crystallize and form dust. And this dust has the ability of depleting the light of stars that happen to be in the background. So if the light of a star that happens to be in the background propagates through the galactic or the intergalactic region that has these little grains of dust, so these little grains of dust will absorb, will deplete that light, and then we see it as this dark dust lane. Like in our atmosphere, when the dark clouds above us happen to have crystals of ice, so these ice crystals will deplete the sunlight, and then we see dark clouds, right? Why dark clouds? Because they are pretty much opaque to the sunlight, and then we don't see the sun, and the clouds appears to be dark. It's not the same situation, but it's the same idea. So the interstellar medium has dust, and this dust depletes optical light. And when we look at galaxies like this one, for instance, we see these dark regions indicating cold regions in the interstellar regions where dust occurs and where maybe stars might even be formed. So another example here in this galaxy that looks like sombrero. Oops, where is it? Oh, it's gone. Oh, it's back here. So see, now we are almost looking edge on these spiral galaxies, and as we look edge on, we see this dark dust lane, pretty much indicating the presence of gas of lower temperature. And again, as we studied stellar evolution in the previous chapter, the main condition for stars to be formed is that the gas that will give rise to star formation is a gas that must have lower temperature. So as the temperature is lower, indicates there is less pressure preventing gravity to clump this gas into stars. So spiral galaxies have three main regions, and I would like to show these three main regions in this picture. The first main region is the so-called bulge. See this kind of a halo region here? This is the bulge. By the way, as I show this to our, since you were there, does it show the pointing hand tool?
Yes.
Yeah. So this is the bulge. The bulge in a spiral galaxy can be as big as the one that I'm showing here, but it can also be quite small as the one over here. See that? The bulge here is much smaller compared with the entire dimension of the galaxy. So let me go back to that one. Look at this. The bulge is almost as big as the entire dimension of the galaxy, whereas in this, not a good representation, as in this galaxy, the bulge is quite small. So the bulge is a region that most of the stars that happen to be found in there, they are evolved stars, right? And in the spiral region, the spiral lanes of these galaxies are gas that is giving rise to star formation. So the type of stars you find in the spiral arms are in general young stars, right? So bulge, like this region, are regions where the stars tend to be evolved, and we call them population 2 stars. Whereas in the disk of the galaxy, like here, in the disk of the galaxy, the stars in there happen to be called population 1, and they are young, relatively young stars. Okay. Now, spiral galaxies are classified as spiral A, B, or C, depending on how big the bulge is compared with the size of the galaxy. So this would be an spiral A galaxy. The bulge is almost as big as the entire galaxy. And a spiral C galaxy, sometimes classified as D galaxy, is one that the bulge is much smaller compared with the entire dimension of the galaxy. There is some sort of an anti-correlation between the size of the bulge and the size of the galaxy, and that will indicate the classification of a spiral galaxy. So let me go to elliptical galaxy. Elliptical galaxies don't show these spiral arms. So in elliptical galaxy, there is a smooth transition between the center of it and the edge of it. So you don't see these dark lanes in there, right? So this is an example, another example of elliptical galaxy, another example of elliptical galaxy. This is not an elliptical galaxy, it's a spiral galaxy. You can see clearly these dark lanes in there. Although I had a search for elliptical galaxy, it pops up a spiral galaxy. In fact, this looks like Andromeda, by the way. So, but this is an elliptical galaxy, has a bright central region, and from the central region to the edge of the galaxy, there is a smooth transition. And in fact, in elliptical galaxy, there is a tendency of the stars in it to be relatively evolved. In fact, elliptical galaxies don't show indications of an active process of star formation. So astronomers point the telescope to elliptical galaxies like this one, that has this smooth transition from the bright region to the outer region, and they don't find these dark lanes, which means there is no cold gas in the body of these galaxies. And in fact, it was found recently that elliptical galaxies tend to be populated by hot gas. In fact, they produce a lot of X-rays as a result of this hot gas that exists in between stars. So elliptical galaxies, what are the interesting situations and characteristics of elliptical galaxies? Well, spiral galaxies, the first one that I show, and I have a picture of one here. So spiral galaxies, they tend to have a size that is kind of a constant, and that is about 100,000 light years. 100,000 light years. So if you go from edge to edge of a spiral galaxy, we are talking about 100,000 light years. Like if you take a beam of light from the edge of the galaxy, it will take about 100,000 years for that beam of light, if it could go uninterrupted, to the other edge to take about 100,000 years to accomplish this and to fulfill this trip. Now, elliptical galaxies, on the contrary, they come up in all possible sizes. So there are the so-called giant elliptical galaxy, and those they're called dwarf elliptical galaxy. So dwarf elliptical galaxy, let me see if I pull up, if I can pull up some image. Dwarf, they look like dwarf elliptical galaxies. They are small in size. Sometimes the number of stars on them are so small that you can almost see through, like in a globular cluster. In a globular cluster, you can see through them, right? There are hundreds of thousands of stars in a globular cluster in our own galaxy, and dwarf galaxies, sometimes they are so dwarf, if I could use that word, that you could see through, and they don't have a significant amount of stars in it. And whereas giant elliptical galaxies, they happen to be oversized, and not only that, they happen to be found in the core, in the very central part of groups of galaxies called clusters of galaxies. So clusters of galaxies that have sometimes thousands of members, thousands of galaxies. In the very central part of these clusters, you find these giant elliptical galaxies that have not only hundreds of billions of stars, but trillions of stars. Isn't that amazing? It blew my mind. It really does. So these are examples of these giant elliptical galaxies. So what astronomers think about this? Well, giant elliptical galaxies, they seem to be formed by mergers. Mergers, let me see if I can see mergers. So when let me see if I can, there you go, let me see if I can play some, one of these important processes that leads to galaxies to be the way they are, galactic mergers. So if you give enough time for a group of galaxies to evolve, gravity locally will attempt to bring these galaxies together and form major, larger galaxies, and they will tend to be elliptical galaxies. So in general, when galaxies first formed, they could be spiral galaxies, 100,000 light years in dimension, pretty much stable. But as these close-by galaxies evolve and interact, especially due to their gravity, well, the gravity interaction, they formed system of giant elliptical galaxies where the cold gas that otherwise would give rise to star formation, this cold gas is entirely depleted, and the rate of star formation is so severe in the beginning of this merger that as we observe them right now in our local time, this process of star formation is pretty much ended. All this cold gas is depleted, and then we ended up having a final giant elliptical galaxy. And they usually they happen to be found in the center of clusters of galaxies. So let me bring our horse PowerPoint. These are two pictures indicating elliptical, spiral galaxy. So again, there are two features that can tell is a telltale of spiral galaxies, and that is the spiral arms and this dark dust lane. So these galaxies, as you can see, the bulge is very small and the size of the galaxies extended. So these galaxies could be an SC galaxy or spiral C galaxy, as opposed to spiral A galaxy, which is one that has the bulge as much as the size of the galaxy itself. This is Andromeda Galaxy with the two companion galaxies called satellite galaxies, one atop and the other one below. And Andromeda Galaxy and our Milky Way galaxy, in fact, are members of what we call a local cluster of galaxies of few dozen members. So in fact, there are 40, 50 members in our local group of galaxy. And in our local group of galaxies, there are two galaxies that are big. One is our Milky Way galaxy, which is a spiral galaxy, and the other one is Andromeda, which is the one in the picture. So surrounding these two major galaxies, Andromeda and Milky Way, there is a host of smaller sized galaxies called satellites, and they are in the process of merging with both Andromeda and Milky Way. And in fact, Andromeda itself is in the process of merging with the Milky Way galaxy. Let me see if I can pull up an animation here. And see the time. It's about 3.5 million years. So in 3.5 million years, I think that's the time scale, Andromeda Galaxy and Milky Way Galaxy will merge. And this merge will occur in such a way that the star itself will not collide because they are too far apart. But the gas that is the cold gas that both galaxies have will be used up to form young stars. So there will be an active process of star formation. Oh, that was not a good one. Wait a second. Yeah, again, as the galaxies initiate its interaction, take a look at the spiral arms. The spiral arms developed as a result of interaction. That's Andromeda here, and our Milky Way is over there. And as they get closer, pay attention to the spiral arms that tend to develop as a result of gravitational interaction. See, now it started appearing there, and the two galaxies merge. Of course, this is a simulation, right? and then eventually the two bulge merge, and as a result there is a mega black hole in the core of these galaxies. So all spiral galaxies and elliptical galaxies of significant size, they do have a massive black hole in their very central part. Our Andromeda galaxy and our Milky Way galaxies both have 3.5 million solar mass black hole in there. So this is a picture of Andromeda galaxy, and Hubble was the one who first who was able, in fact, to indicate that these nebulae, the people have been studying and observing up to 1920. So those nebulae, in fact, were extragalactic objects, were galaxies like our Milky Way that was not part of our Milky Way. And here's an example of spiral galaxies. So this spiral galaxy is called barred because it has a bar going across the bulge, and that's an SBA galaxy. So there is only one spiral arm that comes out of the bar, and it's supposed that 50% or more of the spiral galaxies are a bar. They have a bar across the bulge. There are indications that our Milky Way galaxies has a bar like that one. Now Hubble was the one that creates the so-called tuning fork evolutionary diagram for galaxies. It seems that in the beginning it thought there was some correlation between galactic evolution and the progression from a E0 or elliptical 0 to elliptical 7 galaxies. So elliptical galaxies are classified by the flatness of their structure. So an E0 elliptical galaxy is one that is all spherical, and E7 is one that is all flattened. And they thought that might have some progression from one to another, and eventually from that to the spiral galaxy, SA, SB, SC, or SBA, SBC, SBC, as you can see in this tuning fork diagram. And today, this is not true. There is no such as correspondence between those, so some evolution between an E0 to an E7 and from there to an SBA. So there is not such a thing. Although it, with the current understanding that galaxies merge and they change their morphology, which means spiral galaxies can merge to give rise to elliptical galaxy. So we understand the universe as being a dynamic space where galaxies itself, they change their morphology as they evolve. In this tuning fork diagram, this galaxy in the very middle or connection between elliptical and spiral is called S0. They are called lenticular galaxies. So S0 galaxies are funny because they have characteristics of elliptical and spiral. So they look like spiral because they do have indication of cold gas, but they do not have spiral arms, right? They do not have spiral arms, and but they do have cold gas like spiral, but they don't have dark lanes or as you would expect in spiral arms, and they don't have spiral arms at all. So those are called lenticular galaxies, or called S0. So again, as I mentioned before, the elliptical galaxies, they tend to be giant and they tend to be dwarf. So they come in all possible sizes, and in fact, the amount of dwarf galaxies might be significantly larger than we think it is right now. And we now astronomers are considering that the amount of dwarf galaxies out there are much larger than they previously thought, because as more and more uh, larger and space telescopes, and with better capability of detecting light is pretty much produced and created, astronomers realize, because they have better conditions to observe nowadays, astronomers realize the amount of dwarf galaxies out there could be much larger than we really previously thought. And so that perhaps the number of galaxies out there is not just 100 billion galaxies, but much more. In fact, the latest estimate of the number of galaxies in the observable universe, instead of 100 billions of them, as we were pretty much spreading this number last year, now they are talking about trillions of galaxies in the observable universe as a result of a re-evaluation of the population of these dwarf galaxies. More on elliptical galaxies, so spiral galaxies, I mean. So this is a pinwheel galaxies, M 101 is an interesting galaxy. Is nice to observe. Is almost top on, so you're seeing the galaxies as if you're looking down on it, and then you can see clearly the regions in between the spiral arms and the spiral arms. Major one, there are 1, 2, 3, 4 major spiral arms, and out of these major spiral arms, secondary comes out. How distances to galaxies can be determined? Hubble was the one who did the preliminary work on that subject. He found variable stars in an image of Andromeda galaxy, and this series of insets, May 4, May 9, and May 31st, they indicate a star that whose brightness is changing. So if you have several of these pictures taking over consecutive days, you could measure the brightness and the change in brightness over time, and then you find there is some periodicity on it. And that's what Hubble did. He found that periodicity was consistent with a Cepheid star, and the Cepheid star is one of those variable stars that allow astronomers to measure distances. And when Hubble used that information to determine the distance to where that galaxy was, or that nebula was, he found the distance to be several million light years away. And since our galaxy is just hundreds of thousands of light years, indicate this nebula, in fact, is an extragalactic object. That was the first time that astronomers realized the universe was not confined to the limits of our Milky Way galaxy, but expanded beyond our own Milky Way. And that's the birth of the so-called extragalactic astronomy, an astronomy that deals with the universe in large scale. Now, how do we know distances to galaxies that are very far away? We can use OB associations, the brightness of these associations. We can use Cepheids or Lyra, but we can also use supernovae explosion. So supernova 1A is the result of a binary system consisting of a white dwarf and a binary star that is encircling this white dwarf. So eventually the mass of the companion falls on the white dwarf to the point that the white dwarf itself can't support that weight anymore, any longer, and the white dwarf explodes in a supernova type 1. So the amount of energy released is well known because it's equivalent to the mass of that supernova, which is 1.4 solar mass according to Chandrasekhar. And so astronomers scanned 1.4 times c square mc square, which is the Einstein relation mass energy. So astronomers can then use the inverse square law to determine how far that explosion took place. And because of that, astronomers were able to, with some level of confidence, to, in the last 20 years or so, to determine the universe is not only expanding but also accelerating. And there is some unseen, unknown energy that fills the region in between superclusters of galaxies, which we now call dark energy. So Milton Humansson, he was fantastic. I mean, he's someone that inspires me particularly a lot. He always wanted to be an astronomer, but he didn't have a degree. But he wanted to be somehow involved with astronomy, and for that he got a job being the charioteer in Mount for the 4-meter telescope in Caltech. So the 4-meter telescope was being built, and somebody was hired to take, instruments and parts and all of that to the observatory that was being built on the top of the mountain. And Humansson was the one that got that job. And once no more instrument was required to be taken to the observatory, he was hired as a janitor. And then he did janitorial work in the observatory, and then he started working with astronomers at night. And then pretty soon he was allowed to help them to develop photographic plates. So we are talking about 1920, right? So, and he was the one, although he didn't have no academic instruction, and he was so skillful that pretty soon he became a key player in the process of understanding how the universe expands. So Humansson was the one helping Hubble to classify galaxies, the so-called Hubble flow, which is given in this graphic here, that relates the velocity of galaxies in which we measure galaxies flying away from us, pretty much using Doppler effect, using the skills that Humansson pretty much helped to unveil, and also using the distance to these galaxies that Hubble was able to collect. So Hubble was using Cepheids and information he could get the hands on to determine distance to galaxies, and Humansson was using Doppler effect techniques, which we learned before, to determine the receding velocity of those galaxies. And when they plot that information, they found this very nice curve, which says that the universe is expanding with a rate that is about 70 kilometers per second every 3.2 mega light years, which is phenomenal. So so the work of Hubble and Humansson was what we now call the Hubble flow. Is one of the key points or a key information that indicates the expansion, the universal expansion, and this data hasn't been challenged so far. I mean, that's what it is, and there are several different interpretations. The first one, well, is an explosion. The Big Bang is a big explosion, and then gas is just flying through the space, like if you have a grenade. You explode the grenade, and then you have debris flying out of a point, the point of explosion, in all directions. And then if you are somewhere in the middle of that explosion, you can see all these little debris flying away. That's one interpretation, but that's not the right one. So the correct interpretation is that the space, which is the entity that exists in between the galaxies, or superclusters of galaxies, better saying, the space is the entity that happens to be expanding, inflating. And if that interpretation is bringing to our light, to our view, then this ruler helps to explain what's going on. The ruler on the top, it shows ants separated by 2 units, let's say 2 inches, centimeters, is given in centimeters, I think. So you take 2 to the 4, and then you have another, the second ant is from 2 to 7, so 5, right? 5 units distance. And you have a fourth ant is in the Mark 12, so it's about 10, right? From 2 to 12, you have 10. So if you allow some uniform expansion rate for the space in between the ants, so it's going to be such that if you now take a ruler and measure the separation between the ants after the expansion takes place, you're going to find that the further the ant is, which means the fourth ant, the speed in which you detect its expansion is larger than it is for the ants that are closer by. And that is the explanation of the Hubble flow. The explanation of the Hubble flow is the space is stretching. And as the space is stretched, galaxies that happen to be in space are seen to be aparting and departing from one another at a higher rate if you observe them further and further. And another consequence is no matter where you are in the universe, you see the same thing. You see the same universal expansion. There is not such a thing as a central part of the universe. Like in a grenade, there is not a point where the explosion took place. All places in the universe sees this expansion taking place. Another classical example is the bread and the raisin in it. So as the bread expands because you put it in the oven, all the raisins will see the same phenomena. Raisins that happen to be closer will be expanding and departing with a receding speed that is less than it is of the raisins that happen to be further out. And that is for this chapter, the chapter on galaxies. So basically, there are these 3 broad categories of galaxies: spiral, ellipticals. There is another one that I didn't mention, irregular galaxies, like Magellan clouds you can see in the southern hemisphere. So irregular galaxies doesn't have a specific shape. They do have star formation going on, they do have gas. But the major distinction between spiral and ellipticals is in the process of star formation. Spiral galaxies have star formation going on, like our Andromeda and Milky Way galaxy, and elliptical galaxies do not show any indication of star formation. Elliptical galaxies can be giant or dwarf, and they have this smooth transition between brightness from its very central part to the edge, whereas spiral galaxies don't. Spiral galaxies, they show spiral arms, and they have these bulge regions, the spiral arms region, and the halo regions. Okay? All right. Okay. I will start pulling up in our course this chat, and for the Astro News, read the article, Let me stop taping now. So read the article and give some indication or what do you think the outcome should be once all this technology and information that is being released by this telescope survey, what impact you would expect to happen to population once this information is released. I mean, to people like me and you, we have a computer, we have, computer time, and we have some skills, and we want to find how science operates. Just give your opinion on it.